So we're going to quickly talk about centripetal acceleration, just a reminder, kind of review. Centripetal acceleration is when an object's moving in a circular path, but it's accelerating because it's changing its direction. When we know an object moves in a circle, it's changing its direction the entire time, so it's accelerating the entire time. And anytime you have an object that is changing its direction constantly, it's going to be changing. And you know you can accelerate by changing your speed or your direction. So centripetal acceleration, the formula is VT squared over R. And if you think about it, VT is actually the tangential velocity. It would be...
Sorry, I'm having trouble hearing you.
Siri wants to talk to me, apparently, okay? So go away, Siri. Tangential velocity would be, if an object's moving in a circle, it would be the line perpendicular to the circle at any given point in time. So the velocity is perpendicular. The centripetal acceleration is always toward the center during the entire time. We have centripetal acceleration is measured in meters per second squared, and then the radius is measured in meters. So VT squared over R is your formula. Tangential speed is when we're talking about tangential velocity, we're really talking about tangential speed because the velocity is constantly changing. And then if it's moving at a constant velocity, we call it uniform circular motion. So then we talked about centripetal force, which is the net force that is directed toward the center of the circle. Because there's a centripetal force toward the center, there's going to be a centripetal acceleration toward the center. Just a reminder of Newton's second law, F net equals ma. Well, in this case, when we're dealing with objects that are moving in circles, we don't do F net because F net implies, remember we did F net x and F net y and all that stuff. But in this case, when we do an F net equation, we're going to do an FC equation because its centripetal force is the net force. And we also know, so we would add together any forces that are going toward the center and subtract any forces that are going away from the center. And we'll talk about a specific example today that is like the lab that we're going to do. But centripetal force, in this case, in all cases, is equal to mv. It's actually equal to ma, just like F net equals ma. It's equal to ma, but in this case, it's AC, centripetal acceleration. And we know AC is equal to VT squared over R, which gives us this formula, which is the most common formula, which is mvt squared over R, okay? mv squared over R, which is this formula for centripetal force. Measured in newtons, masses in kilograms, tangential velocity in meters per second, and a radius in meters. If it's in anything else, then you need to convert to it, which today in your lab, your radius is going to be in centimeters. You need to convert to meters. Thank you. And we're going to have to make sure that our velocity is in meters per second. People like to talk about this thing called the centrifugal force, which is it's a fake force. It doesn't exist. What it is they're really talking about the force you feel when you're in an accelerated frame of reference, but really it's just inertia is what you're feeling. And so today we're going to talk about roller coasters. And basically during a roller coaster, when you're going on a loop in a roller coaster, you feel really light at the top and you feel really heavy at the bottom. Well, this is because of this phenomena. Because when there's multiple forces acting on an object that's moving in a circle, you actually have to incorporate the multiple forces into it. And if we look at the force, the formula for centripetal force at the top of a track, you add together all the forces that are going. You can see here, you got centripetal force is equal to normal force plus Fg. The reason behind that is the normal force that the track is pushing on the cart with is toward the center, and Fg is downward or toward the center. So you're adding them together because they're both toward the center. You can see that as they go around, when the track gets back to the bottom, the normal force is still pushing toward the center, but in this case, the gravitational force is opposite away from the center, meaning we have to subtract the gravitational force in our net force formula. And remember, our net force formula is equal to Fc, because the Fc is not a force. It's the net force. It's the sum of all the forces, which we know is going to be toward the center of the circle, because if it wasn't, it wouldn't be moving in a circle. Okay? So you can see that as you move, you're going to go around. At the top, you have the normal force going down and Fg going down. So we would, in this case, we would do normal force plus Fc, and in the bottom, we've got Fc is equal to Fn minus Fg, or minus Fg, because they are going different directions, okay? And so if you look at this, though, if the normal force is actually the force that you feel, right? It's your apparent weight, as it's called. You guys remember when we were in the elevators and we were going up and down and we felt heavy and we felt light at certain points? Fn is really what that is expressing, and we call that apparent weight. Well, in this case, if you were solving for Fn, you would actually get Fc minus Fg. So the centripetal force minus the force due to gravity. Well, if you're subtracting force due to gravity from the centripetal force, you're going to end up with a much smaller Fn than you did before. But at the bottom, you'll see, if you solve for Fn, you get Fc plus Fg. So in this case, you're actually going to end up with a greater normal force. So you feel heavier at the bottom than you do at the top because of that, okay? But today what we're going to do in our lab is we're going to do a problem that looks like this, and we're going to find the normal force acting on the little ball that's going around the ramp. We're going to find it at the top, and we're going to find it at the bottom. So we'd be using these equations. Now, let's look at a practice problem real quick. If you guys could look on your We Do sheet. I want to look at number 5 and number 6, and we'll go through sort of how you would handle this. It says a 450 kilogram roller coaster is at the top of the loop during its ride. If the tangential velocity of the roller coaster cart is 14 meters per second, and the force acting on the cart by the track, what is that? What force is that? If they say the force acting on the cart by the track, what kind of force is it?
Friction force.
Nope.
Wait, force acting on by a car?
Mm-hmm.
Force of car.
Which of these forces would it be? Normal, centripetal, or Fg? It would be the normal force, right? Because the cart is pushing inward. So we've got Fn is equal to 2696 newtons. What is the radius of the loop is what they're asking. So in this case, we ask ourselves, at the bottom of the, or excuse me, at the top of the loop, what does our formula look like? Well, both the forces are toward the center at the top of the loop, as you can see right here. So you've got Fc is equal to Fn plus Fg. In this case, we don't have Fc, but we're going to actually substitute mv squared over r for that. We've got this value, 2696, and we don't have Fg, but we know Fg is equal to mg. So in this case, we're going to plug in our values, 450 times 14 squared over r, that's what we're looking for, 2696 plus our mass, which is 450, times 9.81. So from here, you can see we're only missing one variable. From there, it's just algebra, and you can solve for the missing value, okay? So let's do that real quick. I'll grab my calculator. We'll do that real quick. We've got 14 squared times 450, and I've got 88,200 over r is equal to, and we've got 450 times 9.81, and then we're adding to it 2696, and I get 7,110.5. I multiply both sides by r to eliminate that, so we get 88,200 equals 7110.5 times r, divide by 7110.5, 7110.5, and I get an r that is equal to 88,200 divided by answer. I've got 12.40 meters right there, okay? So that's the type of problem that we're going to be tackling today in both the lab and in this next problem. Before you do your lab, I would like you guys to figure out number 6, which is asking for the normal force at the bottom of the ramp. So it's similar situation, but you got to be able to solve for the normal force at the bottom of the ramp. You now have the radius, so that will help, okay? And you'll be solving for this FM, which will be different, okay? You now have the radius, and you'll be solving for FM, okay? So go ahead and try that, and we'll see how you do.